This video will serve as an introduction to our logarithmic functions, or logarithms as they're simply called, and will also serve as a good review going back and thinking about some of the basics of exponential functions. So that's where we should actually begin. This is where we're actually going to use so many of those properties that we discussed when we did our inverse section. So we have our basic graph that we discussed, that we looked at in section 3.2, a function b to the x, where b is some value greater than 1. That is our basic exponential function. And then using those properties, we saw that no matter what b is, b to the 0 power is 1, so that we get a y-intercept of 1. And then as we put in bigger positive exponents, so if our base was, say, 3, that 3 squared, 3 cubed, 3 to the 4th would give us bigger and bigger values. So on the right side, this shoots up and gets very large in a hurry. But on the left side, as I plug in negative exponents, that I could get these fractional values. That's something like 2 to the negative 1 power is 1/2, 2 to the negative 2 is 1/2 squared, so 1/4. And we end up getting these fractional values. And the more negative the exponent we put in, the smaller the fraction we get, so that we end up getting this horizontal asymptote just on this side, y equals 0. Again, we have our y-intercept, 0, 1, and then on our right side, this goes off to positive infinity as x continues to go to the right to positive infinity as well. So I want to start with this to point out that this new function that we've presented, does pass the horizontal line test, that this is a one-to-one function, so that if this is our original function f, we define the inverse of that function as log base b of x. That is our definition of a logarithm. We are entirely basing our logarithms off the inverse of these original functions. So just jumping down here for a quick moment, we'll come back and talk about the graph for one more in just a moment, and then we'll get back to the basics, the computation and how logarithms work. But just back right here for one moment, our initial discussion of inverses was that if f of a equals b, then f inverse of b equals a, and vice versa. That's why this is really an if and only if, that knowing this leads to this and vice versa, knowing this leads to this. Well, specifically here, the one thing that's a little awkward, I use the b as the base, and I'm intentionally not using the x's and y's because they keep changing roles. So I will use c as my base here. And if this is my original, that c to the a power equals b. That's literally what will be happening in this function. I plug in an exponent, and that exponent would be the x value, and the answer would be whatever we get when we raise that base to that power. Look at how that works in the inverse situation now. So now I still have that same base of c now, but now it would be log base c, and now the b is what you plug in, and the a is the answer. That still looks really ugly, but that is the relationship we have to get used to. So that if 4 squared equals 16, then log base 4 of 16 equals 2. That's really how we're going to understand logarithms. Now, most of us, if we look at our calculators and we think about logarithms, for most people, this is about where their knowledge ends. There's a regular log button. Maybe some people also know a little bit about this natural log, the ln button. But basically, there are a lot of people, that button is the only thing they know about logarithms, but this is the definition. And we'll come back and talk about the calculator a little later and what bases are available, but this definition will go with any base at all. So that our basic understanding of a logarithm, that when we're presented with this problem, that the understanding is that this number to what power equals this, and that is how we get this answer. So I will do some more examples, and we'll come back to that in just a few more minutes, and that's where we'll get a lot of reminders of the properties of exponents, and that'll help us to solve these log problems. But let's come back up here for one more moment and finish discussing the graph. This function was 1-to-1, so that it has a well-defined inverse function. But now, thinking about the base graph for a log, everything flip-flops. What used to be a horizontal asymptote y equals 0 will become a vertical asymptote x equals 0. What used to be a y-intercept 0, 1 becomes an x-intercept 1, 0. And that in general, I only have two ideas there, but the whole way I'm generating the rest of the graph is the flip of this across the line y equals x. So that this part that used to approach the x-axis here would now be approaching the y-axis here. And we'd end up with something like this. This graph is the flip of this graph across the line y equals x. And last couple of quick things we've mentioned, look at the domain here. The domain of an exponential function goes from negative infinity to positive infinity. Goes forever to the left, forever to the right. So the domain of f here, negative infinity to positive infinity. And the range, well, the lowest y, this approaches the x-axis but never touches it. So we approach 0 but don't touch, so that gets a parentheses. And that it goes up forever, so the high value is infinity. So there's our domain and range for f, and now look at the domain and range for f inverse. If we remember our properties, these flip. All the x's in f become all the y's in f inverse, and that's what happens. All the y's in the original f become the x's that we use in f inverse. So just looking at this picture, thinking about the domain of f inverse, well, I'm approaching this vertical asymptote, but I never touch it. So I never quite get to 0, but I approach it on the x-axis. And that this goes forever to the right, to infinity. If we think about the range, well, this goes down forever. So it starts at negative infinity. Now, the highest one, this is a little tricky, because some people come up here, and they almost look at this like it's flattening out. It still keeps increasing. It just goes up very, very slowly. So as you keep going further to the right, this does still keep going up. It certainly doesn't go up as quickly as this did. This goes up in a hurry. This just very slowly just keeps creeping up, up, up. So that also goes up to a y value of infinity. So we've got all of our properties. And in this section, we'll come back and do a little bit more with the graphs. We've mentioned in the notes how to move and sketch these graphs. We'll see similar things here. So we'll do a couple of those. But let's come back and practice these properties and evaluating basic logs. As we go along, we'll get a few other properties to realize to go along with that. But the next section will really focus on those properties. So let's evaluate. And let's start fairly simple. Let's evaluate problem number 1. Let's find log base 2 of 8. As I was saying, this was kind of mentioning up here, every log problem we do in some way connects back to the idea of exponentials. And that's really the idea. In that inverse section, we talked about flipping roles, and that's what we need to get used to here. So we're looking for this. This is some unknown value. How do I find that unknown value? Well, I think about 2 to that unknown value as an exponent would have to equal 8. And now just doing that little bit of work, now even if we're not sure of the answer right now, we've got good things to try. Well, 2 to the first power equals 2. 2 to the second power equals 4. 2 cubed equals 8. Well, if 2 cubed equals 8, that is the answer. Log base 2 of 8 equals 3. Notice at the very end here, the answer is not 2 to the third power. The answer is just the exponent itself. The base comes up here, and the further we go along with these problems, more people get used to not even writing this out, even though that's what they're thinking. They just go right here. 2 to what power equals 8? 2 cubed equals 8. So let's continue. Let's do some more. Number 2, let's look at log base 16 of 4. This will remind us of an exponential property. I'm still going to set up the same thing, 16 to what power equals 4. And right off the bat, that's not an easy thing to think about. A lot of people, it's a common mistake. People think the answer is 2 because 4 squared equals 16, but it's the wrong base. It's the wrong setup. If it was log base 4 of 16, the answer would be 2, but we can't pick and choose which one is the base. The 16 is the base, the 16 is the one that needs the exponent. But think about that. If 4 squared equals 16, what can I do to 16 to get myself back to 4? The opposite. It's not a clean inverse, but it's that same idea. The square root of 16 equals 4. That's the key to solving this. And the last reminder is just to remember that radicals are exponents. That if we have the square root of x, that is the same thing as x to the 1/2 power. And for any radical, that would be the 1 over n power. So that's the way to finish this. The square root of 16 equals 4, and the square root is the same thing as the 1/2 power. Let's move along, do another one. We're going to do several more here. Number 3, let's evaluate log base 3 of 1 over 9. Same idea, 3 to what power equals 1 over 9. And a lot of people come down here and they recognize that 9 is 3 squared. So a little bit of a coincidence, but just very common. Just like in this previous one, a lot of people thought the answer was 2 because of this. And in a similar way, people think the answer is 2 here as well. But the issue is that that 9 is in the denominator. So we need to do something 2, 3 to not only end up with 9, but 9 in the denominator. The 9 is downstairs, that's 1 over 3 squared, and that's what happens when we use a negative exponent. So this answer, it's log base 3 of 1, 9 equals, and that would equal negative 2. 3 to the negative 2 power equals 1 over 9, therefore the answer is negative 2. Now this is only a few examples. I definitely want to do a few more before we get back to the graphs and start moving on to the higher properties of logarithms. But just as you do this, a lot of people start to get a lot of good ideas. There's not too many coincidences here that if your answer is bigger than your base, well, that's where we get our typical exponent. If your inner piece here, we formally call this the argument inside the log function. And if your argument is a fraction, well, that's the result of a negative exponent. And if your argument is smaller, well, that normally comes from doing some radical. It's not always a square root. It might be a cube root or a fourth root, but that's where we'd end up with fractional answers. And by the way, that is why, going back up here, that is why the domain for the exponentials is everything. We may understand a lot more naturally things like 4 squared and 4 cubed, but 4 to the 1/2 power, 4 to the 3/2 power, those fractional exponents have components of radicals. So those do make sense. That's why this function is all connected. There's no breaks and holes. It's not only defined at the whole number values, it's defined for all the fractional and decimal values as well. Those may not always be nice answers. Something like the square root of 4 is a nice clean answer of 2, but something like the square root of 3 is an ugly answer, but we could still use our calculators and see 1.7 blah, blah, blah keeps going, but that still makes sense as a number. Okay, so let's get back down here. Let's evaluate some more log values. Number 4. Let's look at log base 7 of 1. 7 to what power equals 1? This initially can be quite frustrating, trying to think about what am I doing, how does this work? But the simple answer is the 0 power. 7 to the 0 power equals 1. That was one of our generic properties that we discussed for exponentials. Now, 0 to the 0 is something completely different. That's an undefined property. That's a pretty hard calculus problem. But we've already established that our b will always be a number bigger than 1. So that's why in this situation, knowing b will always be some number bigger than 1, anything to the 0 power equals 1. So this answer is 0. That goes back here and understands and re-explains why every basic log function has this x-intercept, the way that it does. Every one of these, doesn't matter what the base is, but the log of any base of 1 equals 0 because b to the 0 power gives us the 1. So going back to this one we just did, well, if that was log base 12 of 1, the answer would be 0. If it was log base 17 of 1, the answer would still be 0 because any of these bases to the 0 power would get us back to 1. Now we've got a couple of special logs to discuss. That all the previous logs we've written, we've always had that generic log base b of x. But when we write that, we always clearly see the base that is given. If we do not have a base written, now, again, this one up here, that was log base b of x, is how you'd formally read that. But now, if you just see plain old log of x, this one has its own special name. This is referred to as the common log. And the common log, well, it's called the common log because it's used very commonly, specifically by engineers, and the common log is base 10. So if you're ever given a problem and it appears like someone forgot to write the log, you just have to know that is the common log and that is base 10. And that is one of the buttons you have on your calculator. Notice all the previous ones, you did not have a log base 2, a log base 16, you do not have a log base 3. None of these buttons are on your calculator. None of these either. But if you just have number 5, let's look at log of 1,000. It's easy to think that I forgot something, but again, no base written, so that means 10 to what power equals 1,000, and that would be 10 to the 3rd power. And that's the first example that if you did that on your calculator, if I use my regular log button, so log 1,000, enter, and there's the answer 3 that we had right here. The last special log is lnx. Now, I like to use my regular print L for all the other logs, but for ln, I tend to use a script, a cursive L. It's perfectly fine to write ln, but just for some reason, this is understood as an L as a log, but for some reason, people start to mistake that as a 1. So it's fine. There's nothing wrong with that. Either way, that's just my common tendency and my way of writing it. So either way you write this is another special log, and this one is called the natural log. For people who focus on engineering, common log is the one they see most frequently, and they stop calling it common log, they just call it log because that's the only one that they really use. For people who continue in math, as math is a focus, this is the one that we use a lot more, the natural log, the ln function. The ln is also based off of a special base, natural log of x is log base e. And what is e? Well, e is just a number. Notice on the calculator, this is not a coincidence. The ln directly above it is the e to the x button, and for the log has the 10 to the x right above it. They're intentionally putting these together to pair them with their specific inverses. So that's what we have here on the calculator, and that's really all we need to understand. E has a lot of uses. E, if you read through the book a little bit, we saw that's the idea of continually compound interest. It has so many other direct applications that we'll see at the end of this chapter. So E is kind of like the number pi. E itself is an ugly number, 2.718. It goes on forever. If you put that in your calculator, I have a separate E button here directly above my divide sign. So I could just do that. And there's my whole number e. But remember, this goes on forever. It doesn't stop here. It just keeps on going, going, going. If I use this button here, I would do second ln, but now it's already looking for an exponent. So e would just be e to the first power, and we still see that same exact answer. So e is like pi. It's a number. It's an ugly number. It goes on forever. So we could approximate it and round it off, but for a lot of our applications, we'd rather use the exact value. And since it's an ugly number, we just give it a symbol, and this is E for Euler. I know that looks funny because it's pronounced Euler, even though it looks like it's Euler, but this is a famous mathematician. He's one of the people that, I mean, he does a lot of work in so many different areas of math, but this number is named after him. So that's all we have to know. And now that we've done that, we can get a list of basic properties. These basic properties are scattered throughout section 3.3, and then we'll get into some more specific problems in our next video discussing 3.4. But some of these basic properties, log base b of b equals 1. Well, think about it. If this was number 5, 5 to what power gives you 5? 5 to the first power. So there's nothing too fancy there. Similarly, we discussed this above but didn't formally write it out. Log base b of 1 would always equal 0. And then there are a few others that we could try and work on, but those are just two big ones that definitely come up. Number 3, there's one problem where they talk about log base b, b to the n equals n. I mean, that's not a surprise at all. This is starting to lead us to the idea of composition and how these two functions clean up and simplify and cancel. We've mentioned the idea that f composed with f inverse is equal to f inverse composed with f, and that simplifies to x. And that's what this property is trying to get to, that if you do these consecutively, they undo each other and cancel. And same thing if I do it in the other direction, b to the log base b of n also equals n. And these are just the two demonstrations of the compositions and how logs and exponentials cancel each other. In this one, the original function, b to a power, is on the inside with the log on the outside, but they cancel and you get n. In this one, now it's this form. Now you've got the inverse, the log on the inside, with the exponential on the outside, but if they happen completely consecutively like this, that they both cancel. This one in particular makes a lot of sense, just based on the definition of a log, but either one, if we just think about simplifying, it doesn't have to just be with numbers. If I had log base 5 of 5 to the x squared plus 3 power, these essentially would cancel, and you're left with x squared plus 3. It doesn't have to just give you x. We can end up getting something much bigger because that's what's left in the exponent. The log with the base, matching bases cancel, so we're left with the exponent, even if it's more than just a plain x. And there's nothing special about the 5 here, just that they are the same base. Flip it, reverse it. If I had 7 raised to the log base 7 of 4 minus 5x, same way, the 7 and the log base 7 would cancel, and we just get 4 minus 5x. The last thing before we go back to the graphs and finish up this section is just to realize that when I simplified both of these, they are no longer in the exponent. This was in the exponent of this 5, but now after they cancel, it's not an exponent anymore, it's back down on our main line. And the same thing right here. All of this was the exponent on this first 7, but after the 7 and the log base 7 canceled, this leftover piece is back down in our main line. So let's wrap up this section. This was page 2. Let's wrap up this section with a few curve sketching problems. Let's sketch curves for the following. Sketch the graphs for the following functions. And as I've always said, for these types of problems, I will give you your bases. And I've already set them up. We've got that y equals b to the x. Looks like this with the two key attributes, where this is the y-intercept and this horizontal asymptote. And then if I have log base b to the x, that we've got this as our base graph. An x-intercept 1, 0 with this vertical asymptote. So using those two base graphs, let's sketch number one. Let's look at f of x equals 7 to the x plus 1 minus 3. Well, which curve is our base graph? For this problem, it's this one. We've got the aspect of a number raised to an exponent, so this is the 7 to the x part. But it's got more. What else does it have? This plus 1, a part of the exponent, the inside part of the function. That plus 1 leads to a shift of left 1. And then this minus 3 is outside of the exponential function. It's outside of the exponent. So that'll lead to a shift of down 3. Well, what are we shifting? How do we move things? Well, we go and we do what we always did. If we had any reflections, which this does not, we would do those first. But now everything moves left 1 and down 3. So this initial key point started right here, but now it goes left 1, down 3. 1, 2, 3. So this used to be my key point. Now it's shifted to here. And then the horizontal asymptote, some people just always remember it's always 1 above or 1 below the point, depending on if we had a flip that came up. But you could still shift it. This was the asymptote. It went left 1. Well, that really doesn't move. It's going left, right already, so that doesn't really move. But it goes down 3. So this initially had a horizontal asymptote, y equals 0. Now it's got one at y equals negative 3. And now this curve right here. As we've always seen in these problems, you know, yes, does it cross the x and y axis? It may not. That's not what I'm focusing on. I'm looking for these two keys, the initial key things that we had here. And this point, even though it seemed important because it was a y-intercept, it really was important because that's where the graph started to take off. Everything here was going up slowly, and then it took off after this point. So that's why that needs to be highlighted. So let's do another one, and then we'll do several more. So now let's look at number 2. Let's look at y equals minus 5 to the x plus 2. 5 to the x, still using my basic exponential as my base curve. But what else is happening here? Well, this negative out in front is a reflection across the x-axis. This plus 2 is outside the function, so that'll lead to a shift of up 2. Have to do the reflection first. So initially, my y-intercept is here, and I'm above the x-axis, but as I flip this down, now I'm at 0, negative 1, and I'm below the x-axis. And this is the key point where it starts to shoot down, where before it used to start to shoot up. But that's only the reflection. I still have to do the up 2. So I'm not done. That's not my final move. That's not my final graph, because I still need to do the up 2. But from here, well, what goes up 2? This did. So now my horizontal asymptote is up here. And my y-intercept was here, but up 2, so now it's here. So I still have my graph going down, but now just with these new setups. Starting on this, swooping down, and that is the final graph to go with that. If that negative was on the inside, that would have been a reflection across the y-axis, not the x, and I would have had something like this. But that one's done. Let's do two more. Number 3. Oh, notice very quickly, f, y, that doesn't matter. I'm looking over here at the equations, and both of these have the basic exponential. That's why we use this as the base graph. Number 3, let's look at g of x is equal to log base 3 of x minus 2 plus 1. Now that's my function. Well, this is a log function. So now I'm using this as my base graph. But this is only plain log x. This has an x minus 2. That minus 2, that is inside the parentheses. That's inside the argument that goes with that log. So that's going to be a shift of right 2 units. And that plus 1 comes at the end outside. So that'll be up 1. So just like I did in this first one with the exponential, I'm going to focus on the key point, which started as the y-intercept. I'm going to do similarly with the log graph with the x-intercept. So we started right here. This is the point we initially cared about. Sorry. Started right here. This is the point we initially cared about. But now I'm going right 2 and up 1. So starting here, right 2, up 1. Now that is the equivalent to this point. But what do I do with that? Well, where is the vertical asymptote? Started here, taking this up 1. Well, it goes up and down, so that doesn't do anything. But moving it right 2 makes a difference. So now this setup, this asymptote, this key point gives us this graph for this logarithm. One more. Number 4. Let's look at h of x is minus ln of x minus 3. Natural log. Any logarithm has this as its base graph. So number 4, still using that as the base. This, oops, I'm sorry. I wanted this negative on the inside this time. Very sorry about that. If I left it the way it was, that would have been a reflection across the x-axis. So this would have become my base graph, and then I would have done any subsequent moves. But I wanted to do one where the negative is on the inside. So this will be a reflection across y. That covers that. And then the minus 3 on the outside, down 3. Do your reflection first. Used to be this, becomes this. And this point used to be 1, 0, so now it's negative 1, 0. But now everything goes down 3. So my key point was here. Now it's down 3. This was the vertical asymptote. Just shifting that down 3 doesn't move. So it stays right here. And there is my final graph.